Imagine stepping into a world that is both familiar and utterly alien, a place where the air feels warmer, forests stretch toward pale polar skies, and giants roam beneath towering conifers. This is the Jurassic, a chapter of Earth's story that lasted more than 50 million years, beginning around 201 million years ago and sliding into the Cretaceous at about 143 million years ago. It sits smack in the middle of the Mesozoic era, the era many people call the Age of Dinosaurs, and it's a time of dramatic recovery, explosive evolution, and shifting continents. Let's take a relaxed, vivid stroll through this period and pull together the big ideas, the drama, and the life that made the Jurassic so remarkable. Start with where the name comes from. The term Jurassic was coined by 19th century scientists studying the limestone layers of the Jura Mountains along the France-Switzerland border. That name stuck, and today it labels a whole period of time and a system of rocks, the ground-level pages of Earth's history book. The Jurassic opens on a note of dramatic change. The boundary between the Triassic and Jurassic is tied to a major extinction event, a reset of sorts. Volcanic activity linked to the breakup of the supercontinent Pangea unleashed huge eruptions. These eruptions are thought to have flicked the atmospheric switch, pumping out gases, triggering climate shifts, and clearing ecological space for new players to rise. From the ashes and chaos, dinosaurs surged in both diversity and dominance on land. Speaking of continents, picture Pangea slowly tearing into pieces. By the start of the Jurassic, rifts had begun dividing the supercontinent into two massive landmasses, Laurasia to the north and Gondwana to the south. Oceans and seaways widened and narrowed, creating shallow inland seas, island archipelagos, and marine corridors that connected distant habitats. The North Atlantic began to open, and the Tethys Ocean stretched between continents. These shifting shorelines and drifting plates helped shape distinct regional ecosystems and allowed life to diversify in different directions. Climate was another defining feature. The Jurassic was generally warmer than today. Estimates suggest global temperatures were perhaps 5 to 10 degrees Celsius higher, and atmospheric carbon dioxide was much greater. Ice sheets at the poles were absent. Forests grew well into high latitudes. But this wasn't a monotonous greenhouse. The period saw climatic swings, warm spikes and cooler intervals, brief cold snaps, and longer warm pulses. The Torsion, an early Jurassic age, was a particularly hot, troubled time marked by oceanic anoxia and acidification, tied to massive volcanic eruptions. Later, Middle Jurassic intervals cooled, then warmed again in the Kimmeridgian, before another cooling toward the end of the time slice. Sea levels responded to these shifts, rising and falling in cycles that left their mark in the rock record. On land, the plant world set the stage. Imagine landscapes dominated by gymnosperms, conifers waving in coastal winds, ginkgo relatives dotting wetter lowlands, and cycads and benitalian shrubs filling sunny clearings. Ferns carpeted the understory. These plant communities lacked flowering plants as we know them. True angiosperms would not become common until the Cretaceous, but many modern conifer families trace their early roots to the Jurassic, showing up in the fossil record in recognizable forms. Some extinct groups, like the benedictales, even evolved complex flower-like reproductive organs and may have been insect-pollinated, a reminder that plant-insect partnerships were already growing more sophisticated. If plants were the stage, animals were the performers. Dinosaurs rose from earlier reptilian cousins to become the dominant land vertebrates. This wasn't a sudden takeover so much as a major rebalancing. In the Triassic, land fauna had been a mix of dinosauromorphs and their distant crocodile cousins. By the Jurassic, dinosaurs held center stage. They diversified into giants and tiny specialists. Long-necked sauropods became the iconic herbivores, reaching colossal sizes and shaping environments simply by their numbers and appetites. Some Jurassic sauropods were among the largest animals to walk the land. Theropods, the mainly carnivorous and often feathered dinosaurs, included forms ranging from primitive, slender hunters to larger predators that patrolled open floodplains. Meanwhile, early ornithischians scratched out niches as small herbivores and armored grazers. One of the most thrilling developments was the rise of aviolans, the earliest relatives of birds. The famous Archaeopteryx from late Jurassic Germany provides a snapshot of this transition. a small dinosaur-like creature with feathers, wings, and a mixture of primitive and bird-like features. The Jurassic thus becomes a laboratory of evolutionary experimentation, where feathers, gliding membranes, and novel body plans appeared in different lineages. The skies, meanwhile, were ruled by pterosaurs, winged reptiles that ranged from tiny insect-eating forms to larger fishing specialists. They were nature's first true masters of powered flight, predating birds. In the oceans, life was no less dynamic. Ichthyosaurs, with fish-like bodies and deeply adapted forms, dominated early on, but many of their lineages thinned out after the early Jurassic. Plesiosaurs, some with long snake-like necks, and others powerful short-necked predators, glided through Jurassic seas. Marine reptiles included pliosaurs that became apex predators, and crocodilomorphs began their evolutionary experiments. Some stayed small and terrestrial, others evolved into aquatic hunters. Fish and sharks also changed in important ways. Ray-finned fishes underwent major diversifications, and the first true teleosts, the group that today includes the majority of modern bony fish, appear near the end of the Jurassic. Modern groups of sharks and rays began to emerge and diversify too, though some ancient lineages like hybodonts still persisted in marginal habitats. Freshwater and small-scale life saw tremendous innovation. Amphibians such as early frogs and salamanders were diversifying, and the earliest crown group frogs appeared during this time. The broader group of lissamphibians, the lineage giving rise to modern frogs, salamanders, and caecilians, expanded into new habitats. Mammalia forms, too, were quietly flourishing in niches often overlooked by dinosaurs. These early mammals and mammal-like relatives were diverse in form and lifestyle. Some were burrowers, others gliders, and a few adapted to semi-aquatic lives. They remained small compared to dinosaurs, but they were evolutionary experimenters, laying down the deep branches that would eventually lead to marsupials, placentals, and monotremes. Insects were evolving alongside plants. The Jurassic saw the rise of beetles in growing numbers, and many modern insect orders were already present. Mouthparts and feeding strategies diversified, permitting more intricate interactions with plants, pollination, herbivory, and predation. Spiders and other arachnids flourished, and the insect world began shaping terrestrial ecosystems in ways that would accelerate in later periods. Beneath the waves, marine invertebrate communities shifted and recovered from earlier crises. Ammonites, with their spiraled shells, became prolific and diverse, serving as important index fossils for geologists. Belemnites, squid-like cephalopods with internal guards, swam the shelves, and bivalves and gastropods diversified into many lifestyles. Coral and sponge reefs expanded in the late Jurassic, though reef composition differed from modern systems, often featuring microbial carbonates and hypercalcified sponges alongside corals. Jurassic life was not immune to crises. The Torsion oceanic anoxic event, for example, created a global ecological shock, widespread oxygen-poor seas, black shales in the rock record, and extinctions among marine invertebrates. This event is linked to volcanic eruptions and greenhouse warming that altered ocean chemistry, triggering acidification and nutrient imbalances. The end of the Jurassic itself is a complicated transition rather than a single dramatic extinction. A time of gradual faunal turnover, sea level changes, and regional differences that still challenge geologists looking for a clear-cut boundary. Our understanding of the Jurassic comes from the rocks and fossils left behind. Stratigraphers divide the period into early, middle, and late epochs, and these are further sliced into stages named after classic fossil localities across Europe and beyond. Ammonites and other marine fossils provide the fine-scale tools for matching rock layers from different places and reconstructing timelines. Yet some boundaries remain surprisingly fuzzy. The line between the Jurassic and Cretaceous is one example where a universal marker hasn't been pinned down, because the evidence varies regionally and lacks a single unmistakable chemical or biological event that shows up everywhere. Jurassic rocks also hold resources and clues to ancient environments. Organic-rich layers like the Kimmeridge clay became the source rocks for modern oil fields. Vast coal deposits formed in some basins, and impact structures buried beneath deserts or sediments tell of cosmic encounters. These records reveal that the Jurassic shaped not just life but the planet's geology and resources in ways that still matter today. As you picture the Jurassic world, think in layers: plate tectonics shifting the continents, seas flooding lowlands and creating shallow marine habitats, a warm but variable climate, forests and cycads painting the land, dinosaurs patrolling plains and riverbanks, early birds testing flight, mammals and amphibians carving out secret lives, and oceans filled with reptilian hunters and a dazzling array of invertebrates. It was a dynamic planet of experimentation and adaptation. This perspective also highlights how interconnected Earth systems are. Volcanism changed the atmosphere and climate, which altered ocean chemistry. Those changes affected marine life and, through feedbacks, the global carbon cycle. Plants and insects co-evolved, shaping each other's evolution. The breakup of Pangea remodeled habitats and migration routes, steering evolutionary paths on separate continents. In short, the Jurassic is a vivid example of Earth operating as a single, interlinked planet. Why does the Jurassic matter to us now? Beyond feeding our imaginations with dinosaurs and dramatic landscapes, it's a period that teaches us about recovery after crises, about how life radiates into open niches, and how climate and tectonics drive big ecological shifts. Studying the Jurassic helps scientists understand long-term climate change, carbon cycles, the rise and fall of groups, and the roots of today's biodiversity. The rocks and fossils preserve episodes, like the torsion event, that echo questions we still face about rapid environmental change and how ecosystems respond. As our walk ends, picture a final montage: a herd of long-necked sauropods moving across a river plain, a small feathered dinosaur skittering through leaf litter, a pterosaur folding its wings against a twilight sky, an ammonite drifting in warm, shallow seas, and tiny mammals scurrying in the underbrush, quietly building a future lineage. The Jurassic wasn't just an era of monsters. It was a time of transformation, innovation, and the slow, patient reweaving of life's tapestry. If you carry one thought away, let it be this: the Jurassic shows life's resilience and inventiveness. It's a reminder that Earth's story is one of change, sometimes sudden, sometimes gradual, and that each chapter leaves traces that can teach us about our planet's past and perhaps guide how we think about its future. Thanks for taking this stroll back in time. Keep your curiosity alive. The rocks have more stories to tell, and we're only just beginning to read them.